Okay, so you should have all this written down. As we go through it, I'm just going to draw the pictures and explain what you wrote down. So first, perpendicular bisector. We've already talked about this before. It's when you have a segment. The perpendicular bisector breaks that segment exactly in half, and it's also perpendicular to it. So it makes a 90-degree angle, and then each side of that segment is the same length. So the perpendicular bisectors not only make a 90-degree angle, but they break it exactly in half. Then the next word is concurrent lines. It's 3 lines that intersect at one point. So it looks like this. How do you go that fast?
Oh, I don't think it's him.
Oh, it's somebody else. Welcome back. No. Was it a beast? The test. They always make yeah. They seem really hard. It's crazy. It's crazy hard. That's what I was telling everybody to try to do well on that PSAT. Because you can get stuck in those tests. And geometry EOC isn't a sure thing either. Like if you feel good at geometry, that's good, but the questions are really, really challenging. Okay. Point of concurrency. The point where concurrent lines intersect. So we drew concurrent lines here. The point where they intersect is the point of concurrency. Circumcenter, where perpendicular. Okay, circumcenter where perpendicular bisectors intersect in a triangle. So if you were to draw a perpendicular bisector from each side, so this line is a perpendicular bisector to this line, this here is a perpendicular bisector to this one, and this here, where they intersect is called the circumcenter. And incenter. If you have a triangle, the point that's equidistant from all the sides is called the incenter. Sometimes you'll see it with a circle. It's also the center of this circle too. If you have an inscribed circle, the center would be the incenter. Next one, perpendicular bisector theorem. So I'm going to label this triangle A, B, C. And then I'm going to draw a perpendicular bisector that bisects line AB. So that means this is the same length as this. What also happens is that AC is congruent to CB. Oh, I forgot to. This point right here is D. And then I'm going to quickly write it in words as well. If segment CD is a perpendicular bisector of segment AB, then AC is congruent to CB. So you'll notice throughout these there's a lot of congruent parts. Circumcenter theorem. We talked about circumcenter up here. It's when, let me use a different color, the perpendicular bisectors intersect at that circumcenter. That's your circumcenter. But what it's saying here is that that circumcenter is equidistant to the vertices. So once you have the circumcenter, it's the same length to each of the corners. Oh, I didn't realize you couldn't see that there. angle bisector theorem and its converse. If a point is on the bisector of an angle, then it's equidistant from the sides. What the heck does that mean? If you have an angle bisector, if you were to take any point on that angle bisector, it would be the same distance to the sides of the angle. So this would be the same length here. And because it's an angle bisector, obviously this is the same measure as this. And the last one, in-center theorem. This one says that the angle bisectors of a triangle intersect at the in-center. So angle bisector of each angle. So if I were to bisect this angle and this one, this would be the in-center. And then it's saying that that in-center is equidistant to the sides. So from the in-center, if you were to draw a line to the sides, all these lines would be the same measure. And that's it. So from here, we're going to move over to the workbook, 5-1, and you'll find those problems are actually pretty easy. It's just about applying the definitions.